Looking back at gas stoichiometry, we're going to do some practice problems because the best way to learn this stuff is just to practice it. So again, gas stoichiometry is just regular stoichiometry with gas laws built in. So in addition to mass to mole conversions, you'll have volume to mole conversions. And you can use ideal gas law to do that for every problem, or it helps also, or if you know it's at STP, you can use ideal gas law for all your volume to mole conversions. But if it's STP conditions, the standard volume is going to be 22.4 liters, so you can use that to figure out how many moles you want if you don't want to use ideal gas law. And we'll do a couple of those practice problems. But if it's non-STP conditions, we have to use PV equals nRT to do our conversions. So with that said, best way to learn this stuff is to practice it. So let's jump straight into it. First problem, we're going to keep it real simple. We're going to do a volume to volume at STP. Now if you remember, at volume to volume at STP, you can simply just multiply your initial volume by the mole ratio and get your answer. But we're going to work through the entire process just to justify that. So let's do that. So our problem says, what volume of carbon dioxide will be produced from the combustion of 10 liters of methane at STP? So I'm looking for what volume of carbon dioxide. So I'm looking for the liters of carbon dioxide will be produced from the combustion of 10 liters of methane. So CH4 is methane. I got 10 liters. And we're at STP. So I'm just going to indicate I'm at STP. Standard pressure is 1 atmosphere. Standard temperature is 273 kelvins. You can put that into ideal gas law if you want to, but I'm going to do a different method. I'm going to use 22.4 liters to do my conversion. So let's convert this 10 liters of methane into liters of carbon dioxide. So I got 10 liters of methane. I'm going to put that over 1. So I got to change liters to moles. Liters go on bottom since it is on top at the start. Means moles go on top. So 1 mole of methane will take up 22.4 liters. There's that conversion factor. So that'll cancel out my liters of methane, leaving me with moles of methane. Once I got moles of methane, I want to convert it to moles of carbon dioxide. So let's set up another proportion. So moles of methane go on bottom since it was on top. Moles of carbon dioxide goes on top. Moles of methane cancel out, leaves me with moles of carbon dioxide, but first I do need some values here. That's your balanced equation. There is 1 methane for every 1 carbon dioxide. So that's a 1-to-1 ratio. Now once I got moles of carbon dioxide, I need volume of carbon dioxide. Since moles of carbon dioxide is on top, I'm going to put moles of carbon dioxide on bottom and liters of carbon dioxide on top. Need some values here. Well, 1 mole of carbon dioxide is 22.4 liters of carbon dioxide. So that'll cancel out my moles of carbon dioxide, leaving me with liters of carbon dioxide. So this 22.4 is canceled out with this 22.4. That leaves me with my initial volume amount of 10, the mole ratio, and liters of carbon dioxide. So that's what I was saying earlier. When you do a volume to volume at STP, all you really have to do is multiply by the mole ratio because everything cancels out except for the mole ratio, your initial volume, and the liters of what you're looking for. So we got 10 times 1 times 1 divided by 1 divided by 1, and we get 10 liters of CO2. And there is our answer. What volume of carbon dioxide at STP is produced if 20 grams of calcium carbonate is heated? Alright, let's pick out our information. So we are at STP, standard temperature and pressure. We're looking for volume of carbon dioxide. So I'm looking for the liters of CO2 if 20 grams of calcium carbonate is heated. So CaCO3 is calcium carbonate. I got 20 grams of it. So we're doing mass to volume at STP. So for the volume to moles or moles to volume conversions, you can use ideal gas law if you choose, and it'll always work. But since it's STP, I'm going to use that 22.4 moles per liter conversion factor. So let's get this thing started. So I got 20 grams calcium carbonate. And that's going to be over 1. I got to change grams to moles. We've done that plenty of times before. We know that moles go on top, grams go on bottom. Well, 1 mole of calcium carbonate is how many grams? So let's look up the molar mass of that. So look at my periodic table. Calcium is 40. I am rounding to the nearest whole number. Oxygen is 16, and there's 3 of them. So 16 times 3 gives me 48, plus another 40. Molar mass is 88 grams for calcium carbonate. Grams of calcium carbonate will cancel out. Once I got moles of calcium carbonate, I need to change it to moles of carbon dioxide. So I'll set up my next proportion. Moles of calcium carbonate go on bottom. Moles carbon dioxide go on top. I need some values here. That's your balanced equation. So that again is a 1-to-1 ratio because there's 1 calcium carbonate for every 1 carbon dioxide. Moles of calcium carbonate will cancel out. Once I got moles of carbon dioxide, I want volume of carbon dioxide. So moles CO2 go on bottom. Liters of CO2 go on top. So 1 mole of CO2, since it's STP, is going to be 22.4 liters. That'll cancel out my moles of CO2. And now I can just do some math. So 20 times 1 divided by 88. I get 0.227 times 1 divided by 1 times 22.4 divided by 1. And we get 5.1 liters of CO2. And there's that answer. Alright, next problem. If 50 grams of sodium is reacted with 30 liters of chlorine gas at STP, then how much sodium chloride can be produced by mass? So first thing I notice is I have a quantity for 2 reactants. If I have a quantity for 2 reactants, that means one of them is limiting. So first I got to figure out which one is a limiting reactant in order to figure out which one to use for my stoichiometry. So let's do some mole conversions for that one. So first we'll do sodium. We got 50 grams of sodium. Put that over 1. So 1 mole of sodium is equal to 23 grams of sodium. So that cancels my grams of sodium. 50 divided by 23 gives me 2.17. That's going to be 2.17 moles of sodium. Now I can do chlorine. Since this is STP, I can use my 22.4 conversion factor. So I got 30 liters of chlorine gas. Put that over 1. So 1 mole of chlorine gas will be 22.4 liters of chlorine gas. Liters of chlorine gas cancels out. 30 divided by 22.4 gives me 1.34. 1.34 moles of chlorine gas. Now we got to set up our dimensional analysis to figure out how much of one reactant do I need to completely react the other reactant, or to say how much chlorine gas will I need to fully react sodium. Let's do that. Let's slide down a little bit so I got room to work. The question is, if I have 2.17 moles of sodium, how many moles of chlorine gas will I need to fully react this amount? So let's set up that proportion. So since moles of sodium is on top, moles of sodium go on bottom, and I'm changing it to moles of chlorine, so it goes on top. Now I need some values here. That's your balanced equation. So we go back up. I got 2 sodiums for every 1 chlorine. So 2 sodiums for every 1 chlorine. Moles of sodium will cancel. So 2.17 times 1 divided by 2 tells me I need 1.09 moles of chlorine gas. Well, how much do I have? I got 1.34 moles of it. I need 1.09. I got 1.34. This right number is larger. That means chlorine gas is excess. And if chlorine gas is excess, sodium is limiting. So this is your excess reactant. This is your limiting reactant. So I'm going to use 2.17 moles of sodium for any stoichiometry past this point. So now that I know which one's my limiting, I can figure out my question. How much sodium chloride can be produced by mass? So this is my actual question, and we're looking for grams for the mass of it. So I'm going from sodium to sodium chloride. That is a 2-to-2 ratio. And I'll hang on to that information for a little bit later. So let's slide down and figure this out. So I got 2.17 moles of sodium, and I need to take it to sodium chloride. So since it's already in moles, we already got one step done. We just need to do a mole ratio. We're going from moles of sodium to moles of sodium chloride. So moles of sodium go on bottom, moles of sodium chloride go on top, and we said there's 2 sodium for every 2 sodium chloride, so it's a 2-to-2 ratio. That takes care of moles of sodium. Once I got moles of sodium chloride, I got to change that to grams of sodium chloride. So moles sodium chloride go on bottom. Grams of sodium chloride will go on top. Well, 1 mole of sodium chloride is how many grams? Sodium is 23, chlorine is 35. That is 58 grams for its molar mass. That cancels moles of sodium chloride. Now we can figure it out. So 2.17 times 2 divided by 2 times 58 divided by 1. And I get 126.1 grams of sodium chloride. And there is my answer. Alright, next problem. It says, what volume of oxygen gas at 27 degrees Celsius and 2 atmospheres is needed for the complete combustion of 10 liters of propane? So it's a volume to volume problem again, but this time it's not STP. So we got to use ideal gas law to do our moles to volume and volume to mole conversions. So it says, what volume of oxygen gas, so that's going to be O2, I'm looking for the liters, from the complete combustion of 10 liters of propane. It says we got a pressure of 2 atmospheres and a temperature of 27 degrees Celsius. We got to change that to Kelvin. We add 273, and that should be 300 Kelvin even. Alright, so first we got to change this 10 liters to moles. In order to do that, we use ideal gas law, or PV equals nRT. So my pressure is 2, my volume is 10, moles is what I'm looking for, or since this is atmospheres, 0.0821, temperature is 300, so 2 times 10 is 20, 300 times 0.0821 is 2463, times x makes it 24.63x. We divide by the side with x, so 2463 cancels out. 20 divided by 24.63 equals 0.81. And that's going to be moles now of propane. Now that's not our answer, that's just one of our steps. So now we got to take moles of propane and convert it to moles of oxygen. So let's set that up. So if I got 0.81 moles of propane, put that over 1, I change it to moles of oxygen. So moles of propane go on bottom, moles of oxygen go on top. We need some values here, so that's our balanced equation ratio. It's 1 propane for every 5 oxygens. So 1 propane for every 5 oxygens. That cancels moles of propane. Gives moles of oxygen, but I can't set up another proportion since I got to use ideal gas law. So once I get this value, I'm going to stick it into PV equals nRT. So I got 0.81 times 5 divided by 1. That is 4.05 moles of oxygen gas. Now take that value, stick it back into PV equals nRT. So PV equals nRT. Our pressure and temperature hasn't changed. So pressure is 2, temperature is 300. Pressure is 2, temperature is 300. So P is 2. V is what I'm looking for this time. N is 4.05. R is 0.0821. Temperature is 300. 2 times X is 2X. 4.05 times 0.0821 times 300 gives me 99.75. Divide by the value with X, that cancels. 99.75 divided by 2 gives me 49.88. And we said we were looking for volume, so that will be liters of O2. And there is our answer. Alright, last problem. If 6 liters of ammonia at 30 degrees Celsius and 1 atmosphere is combined with 4 liters of hydrogen chloride at 20 degrees Celsius and 2.5 atmospheres, what mass of ammonium chloride will be produced? There's a lot going on with this problem. We got 2 quantities for reactants. We got to figure out a limiting. Both of my gases are at different conditions. So we got to use ideal gas law for them both with their respective conditions. So I got 6 liters of ammonia at 30 degrees Celsius, 1 atmosphere. I got 4 liters of hydrogen chloride at 20 degrees Celsius, and 2.5 atmospheres. I'm looking for the mass of ammonium chloride. So let's figure out the moles of each first, so we can figure out the limiting reactant. So I'd be using PV equals nRT for ammonia. So the pressure is 1. The volume is 6. N is what I'm looking for. R is 0.0821 since it's in atmospheres. The temperature needs to be converted to kelvins. 30 plus 273 is 303. 1 times 6 is 6. 303 times 0.0821 is 24.88. X, I divide by 24.88. That cancels. X is 6 divided by 24.88. I get 0.24. 0.24 moles of ammonia. There's our first one. Do the same thing again for hydrogen chloride. Pressure for it is 2.5. Volume is 4. N is what I'm looking for. R is 0.0821. Temperature is 20 plus 273, so 293. 2.5 times 4 is 10. 0.0821 times 293 times x is 24.05x. We divide by that value. That cancels. 10 divided by 24.05 gives me 0.42. So 0.42 moles of hydrogen chloride. Now that I got the moles for both of them, I got to figure out which one is my limiting reactant. So thankfully we have a 1-to-1 ratio for everything. Makes it a little bit easier. So if it's all a 1-to-1 ratio, the limiting reactant should be the smaller mole amount. So it should be ammonia, but we'll double check it just to make sure. So what we're going to do is we're going to figure out how much hydrogen chloride do we need to fully react 0.24 moles of ammonia. So if I got 0.24 moles of ammonia, that over 1, I need to change it to moles of hydrogen chloride. So moles of NH3 go on bottom, moles of HCl go on top, and we said it's a 1-to-1 ratio. Moles of ammonia cancel out. 0.24 times 1 divided by 1 is 0.24 moles of HCl. I need 0.24 moles of HCl. I have 0.42 moles. Which value is larger? On the right is larger. That means it's excess. So that means ammonia is the limiting. So ammonia is the limiting reactant. Hydrogen chloride is the excess reactant. So any stoichiometry, I will use ammonia. I will use 0.24 moles of ammonia to figure out how much ammonium chloride will I produce. And that is a 1-to-1 ratio. So let's slide back down and figure that out. So once again, we got 0.24 moles of ammonia. And I need to change this to grams of ammonium chloride. So I set up my mole ratio of ammonia to ammonium chloride, and that was a 1-to-1 ratio. That cancels moles of ammonia. Now I got to figure out a mole to mass conversion. So moles of ammonium chloride go on bottom, and grams of NH4Cl go on top. So 1 mole of ammonium chloride is how many grams? Well, chlorine is 35, hydrogen is 1, there's 4 of them, and nitrogen is 14. So 35 plus 4 plus 14 gives 53 grams per mole. So this will cancel out. So 0.24 times 1 divided by 1 times 53 divided by 1 gives me 12.72 grams of NH4Cl, and there is our answer. So just like all the rest of the stoichiometry concepts and lessons, just make sure you get good practice in. That way you can get better at it, not making mistakes. Hope this video helps, and as always, good luck on your tests.